Okay. Okay. Let's work on this. Okay. As you heard during the class, primarily when we start to talk about correlation and regression, we're usually talking about two numerical variables. All the other tests that we worked with a numerical variable and a categorical variable, like different categories that we were comparing, like males and females for blood pressure, different age groups for the rate of diabetes, for instance. So most of the time we're working with categorical variables when we use chi-square, odds ratio, so on and so forth. We're working with categorical and numerical variables when we use t-test, analysis of variance, right? Because the numerical variable part of it is usually an average. That's usually how we're organizing and understanding numerical variables, is we're calculating an average for those variables. This is a little bit different. In this case, we're looking at a situation where we have two numerical variables, two things that we can measure using a number, and we want to see if there's an association between those two things. We're going to start with she's really kind of skipped over this idea of correlation. Correlation is nice because it's a nice English word people understand. Correlation. Regression comes from the word regression comes from the guy that invented this, and it has nothing to do with what it really is. He was, just so you know, he was studying. I don't remember if he was working with plants or people, but he was working, for instance, with the idea that if two people that are very tall have a child, the chances are that that child is not likely to be taller than they are. If two people who are very short have a child, it's more likely that they're going to have a child that's taller than they are rather than shorter than them, because they already are at the low end of normal distribution. So it's more likely to get something closer to the normal rather than further away from the normal. That's called regression to the mean. So while he was working on this, he was dealing with a lot of numbers and statistics. He developed this thing called regression, where he could look for an association between numbers, these numbers versus those numbers. Okay, so regression has to do not with the word regression, but for something entirely different that it's associated with, right? So forget this idea of regression, of why we use regression, why we use the name regression, but just consider the process of regression. So correlation, though, means what it sounds like. We're looking for a correlation. So for instance, and correlation doesn't mean that one thing is the cause of something else, just means that they're associated. For instance, if I told you that the amount of damage in dollars that is caused by a fire is correlated to the number of firemen that show up to the fire, would you say that that's plausible? Right? Makes sense, doesn't it? Right? Are the firemen causing the damage? Sometimes, yes. I know guys that are firemen, they cause a lot of damage sometimes. But usually the deal is a lot of fire. If there's a big fire, a lot of damage, and a lot of firemen show up, right? So there's an association, there's a correlation between the number of firemen that show up and the amount of damage that occurs, right? So the correlation is true, but it's not causative. In other words, the number of firemen not causing the damage, just happens that they're both there in larger numbers because of the size of the fire. So in this case, we're looking at the number of lung cancers in these different countries, and the number of cigarettes, the rate of cigarette smoking in each one, per capita rate of cigarette smoking per year, I guess, and so on and so forth. And we're wondering whether the rate of lung cancer is associated with the rate that people smoke at. Makes sense, right? So people smoke more cigarettes. We think maybe there's an association between the two. So we want to show that association really exists. Okay, and if it does, if we can demonstrate that, we can say to ourselves, well, gee, we've just demonstrated that there really is a correlation or association between these two things. Anytime we start off with this stuff, we're always starting with a null hypothesis. There's no association between cigarette smoking rates and lung cancer rates in different countries. That's our null hypothesis. Our alternative hypothesis is is that there is an association, just like we would for anything else. Okay, so one of the first ways we're going to look at this is we're going to create a scatter plot. Right, scatter plot's a little bit different than a lot of the other the graphs that we use, the bar charts and the histograms and so on and so forth, and the box plots. With the bar chart, what we're doing is we're taking two axes, an x-axis and a y-axis. Correlation, it doesn't matter which one you put on which axis, you're going to get the same result in terms of like test for correlation. So it doesn't matter which axis you use. When we do regression, we tend to like to put the one that's causing the problem on the x-axis, calling that the independent variable or the causative variable. And we put the resulting variable on the y-axis or the dependent variable. In other words, the number of lung cancer cases per 100,000 are caused by the rate of cigarette smoking. The independent variable, dependent variable. This depends on the dependent variable depends on how big the independent variable is. So for now, I'm putting it this way because it makes sense, right? That this is the independent variable and that's the dependent variable. This is the cause, that's the resulting variable. I'm putting it this way not because I need to for correlation, but only because in the long term it's going to be easier for me to deal with it. Okay, so how do we plot this data? Well, we take each data point represents two numbers, an x and a y point, right? So this represents, and you can tell me which country this is. It's a country with the lowest smoking rate. This represents an average rate of smoking of, it looks like about 220 cigarettes per year, and a lung cancer rate of about 6 per million in that population. Which one is that? Anybody notice what that is? 230 is Iceland, okay? And it's 230. Whoops. Can't push that up. It's 230 and 6. And you guys know that I could write that in parentheses as 230, comma 6, x and comma y. Right? You guys remember that, right? From, I know this is ancient history, right? Mostly this was like, what, 7th grade or something like that. Right, when last time we dealt with scatter plots like this, XY plots, right? Don't feel bad. It's been a long time, right? So over here, the highest rate of smoking is this country right here. And you know, kind of odd because this country has the highest rate of deaths, lung cancer mortality. And this country has the highest rate of smoking. They're both high, but this one's kind of like an outlier almost, isn't it? If you were going to draw a line through here, you'd probably draw it like this. So let's take a look at this country. Let's take a look at this country here. That's 1,300. That's the United States, right? Right. We smoke at that time in 1930. The per capita rate of smoking was 1,300 cigarettes per person, right? And the lung cancer rate, mortality due to lung cancer was about 20 per million per year. Okay, what about that one up there, the highest rate, which is, what would that be? That is Great Britain, and that's they smoke 1,100, but they smoke less, but they have a higher lung cancer rate. 1,100, they smoke less, but they have a higher lung cancer rate. Anybody know why that might be? Think for a second. This is 1930. What were most people in Britain using to heat their house and cook in 1930? Coal. Have you guys ever read about the problem that they had for several months, where they had a thermal inversion and they had an issue with like the air becoming toxic for months at a time in Great Britain? People were dying of asthma and emphysema and so at enormously high rates. It's quite possible that might account for this being an outlier. In other words, the lung cancer rate is being confounded by the fact that they had so many other environmental factors that were influencing their lung cancer rate as well. So maybe this is the outlier, not the others. So then, if we look at this, we can almost draw a line through here, right? And it looks kind of like that there is an association here. The more you smoke, the more likely you are, the higher rate that country is going to have lung cancer. Everybody agree there's some kind of association here, right? Okay, so an association starts even down here. We were just talking about this with someone a moment ago. In environmental occupational health science, we talk about something called permissible exposure limits. That's OSHA sets those, and that's the level at which you can be legally exposed to some toxic material on the job site before you have to take some action to protect the worker, like protective equipment, or even better yet, engineering out, the hazard or something like that. It's called permissible exposure limit. It's an average level of some material in the air, right, like carbon monoxide or toluene or acetone or something like that. Average over an 8-hour workplace day that you're allowed to be exposed to in the workplace. There's another organization now that's a negotiated standard. In other words, that's not necessarily a protective standard. It's a negotiated standard because between industry and NIOSH, they settled on a number that industry felt that they could meet. So not always completely protective. Another organization issues something called threshold limit values. Threshold limit value is basically something that medically you say to yourself, you can tolerate this level of exposure and not see health effects. So when you use the threshold limit value, it's usually lower than the permissible exposure limit, but you know that up to that point, it's likely you won't see a significant health effect from that exposure, threshold limit value, right? So now the thing with cancers, unlike most other kinds of exposure, like if you're exposed to a carbon monoxide, if it's low levels, your body recovers from it. The next day you're back at work, like if it's 5 or 9 or 15 ppm of carbon monoxide, you're back at work, your body is recovered from it. If it gets too high, your body doesn't recover, so you start to see that threshold effect. In other words, no health effect, but then as you get too high, you start to see it go up. With carcinogens, there is no threshold effect. In other words, no matter what the exposure is, you'll see an increase in risk. It might be a small increase in risk, but it's not like it's, like smoking 20 cigarettes, but smoking 50 cigarettes or 100 cigarettes doesn't show any increase in risk, and then all of a sudden when you get to 200, it starts to go up. That's the way carcinogens tend to work. So one of the things we see here is that, we see that it's got no threshold effect, and it looks linear, right? And it looks like there's a strong association. So in my head, I'm thinking that is a correlation. There's a correlation between this number and this number. Okay, so now let's take a closer look. The only problem is we can't just look at this on a scatter plot. Scatter plot's a great way to start if you don't know if there's an association or not. Creating a scatter plot like this is a great way to start because then you have a feeling whether you're going to be likely to find an association before you spend a lot of time on analysis, or you go back and collect a lot more data. Okay, so one of the things we're looking at when we're looking at correlation is we're looking at the strength of the association. So in some cases, right? In some cases, in some cases you'll see the data is really kind of tightly associated. So it's almost like a real tight straight line. If I draw a straight line, I'm just going to ignore this part. If we draw a straight line through here, all of these values are very close to that straight line. That's a pretty good association, right? Now, in other cases, it won't be quite as good, right? In other words, it won't be quite as clear. You might get a big cloud of things here so that, there's in a single line that you can kind of see that there is an increase, but it's kind of hard to put a handle on how good an association it is. One of the problems with correlation and scatter plots is that you should not use your eye to judge it completely. That's why we actually calculate correlations. We calculate that R value. These two things are the same numbers plotted on different scales. Down here, the scales are compressed, so it pulls these numbers together. So looking at that, you'd say, gee, this looks like a stronger correlation than that is, but they're exactly the same numbers, just plotted on a different scale. Okay, so if we had reversed the scales, we didn't care, we didn't know which one was the causative one. If we reversed the scales, it would just change the direction of this, but it would still look the same, right? It still look like there's a correlation. Okay, so some correlations are spurious. Okay, what do we mean by spurious? In other words, they just happen in a coincidence, but there's not a good reason for them, or there's some confounding factor. Okay, I just want to show you this. So you guys, maybe it'll make you feel a little bit better about correlations and stuff like that. if you can see some that are a little bit interesting. See if I can't find it. I may have to actually Google it. I must have another folder here with the same name, because stuff I put in there last night's not there. Spurious. There's a guy on the internet that collects these spurious correlations. He looks for data that where he can find two variables that appear to be associated, but it just doesn't make any sense that they're associated, and it just happens by coincidence. This is his site. Okay, suicides by hanging, strangulation, and suffocation compared to U.S. spending on science, space, and technology. Pretty close association there, right? Does that mean one's causing the other? Strong correlation, but not necessarily caused by the same thing. Number of people who drowned falling into a pool, and the number of films Nicolas Cage appeared in that year. How about number of people who died by becoming tangled in their bed sheets, and the per capita consumption of cheese? Almost a perfect association over about how many years? Over 10 years. Right? So not all of these things, I'll put this link on here if you want to go back over it, have a little bit of fun with it. But not all associations are causative. Okay, so now once we see that, now we're gonna wind up moving on from correlations to regression. And in regression, what we're interested in is we're interested in taking this association between these two values. And once we agree that we've proven that there is an association there, we might say to ourselves, well, gee, now that we know that, maybe we can make something useful for this. We can create a formula that'll help us understand how a health intervention might affect this outcome. Right? So, for instance, if I were to assume that this is a straight line, that we can represent this with a straight line, we can draw a formula for a straight line. We can create a formula for a straight line. Anybody remember what the formula for a straight line is? In algebra, remember, is equal to y is equal to mx plus b. M was equal to the slope, and b was equal to the y-intercept. Well, why is that? Well, the y-intercept is the place where the line crosses 0, right? So I'm not going to use this line. I'm going to make my own line over here somewhere. Let's say the line goes through here, right? So if I know that the line goes through 0, and I know the slope, I can draw that line. If I know those two things, the slope and the place where it crosses the y-intercept, then it's a given line. Can't be two lines like that. It can only be one line that satisfies both those conditions. Are you okay with that? In other words, if the slope is 2, that's about a slope of 2. If the slope is 2 and it goes and the y-intercept is 20, the line's going to look like that. If the same slope with a y-intercept of 10, it's going to be this line, right? And this y-intercept with a slope of 1 is going to look like that. With a slope of 1/2, it's going to look like that, right? You know those two factors, you know the line. So you have y is equal to, for instance, the one I just described, 2, the slope, x plus 20. You have the formula that represents the line, which approximates all this. Right? What does that mean? That means if I told you how many cigarettes were consumed, what the per capita consumption of cigarettes were in some other country that we didn't do the data for, that we didn't spend $1 million collecting data on, you could predict what the cancer rate might be in that country without actually having to do the statistical, without having to calculate all the statistics and save $1 million, right? Unless there's other confounding factors or something like that. That's the strength of this, right? Is that now you can make predictions that save you money on doing other research. The other strength of this is that, what does that slope mean? That slope means how fast the lung cancer rate goes up relative to how many more cigarettes people are smoking. So, for instance, if the slope of this is approximately 1, I would say, right? So 10, 20, 30, so it's about a 45-degree angle here. Slope is about 1. So, look at this. If a country where they smoke 600 cigarettes per year, right, looks like the cancer rates there are about 25 per million. Lung cancer rates, 25 per million. In countries where they smoke 1,200 cigarettes per year, the cancer rates look like they're about 40, 25 to 40. So it looks like if I can get people to cut their, reduce their cigarette consumption from 1,200 cigarettes a year to 600 cigarettes a year, I can save 15 lung cancer mortalities per year. I can tell from the slope whether a small change here, right? If it's a big slope like this, a small change here makes a big change here in that part, in the y-axis. But a flat slope like this, well, a small change, a big change, even a big change in the x-axis, the number of cigarettes smoked, if it's a flat slope, it's not going to make much difference in the outcome. So I know that, gee, if I spend my public health dollars in getting smokers, even if I can't get them to quit, getting them to reduce the number of cigarettes they smoke a year, so the average per capita goes down per year, I can have a big effect. Or maybe it won't have that big effect. So maybe I should spend my money on other things like getting them to quit entirely, better diagnostics, and so on and so forth. Right? So that slope's an important thing. That's really why we're doing all this. Okay, so let's actually go ahead and do some of this stuff. Here's our y is equal to mx. So I'm going to use, I have a few data sets. I'm not sure why. Here's one. Here's the data set we have here. This is a BMI. Well, actually, I'll show it to you. It's a bunch of numerical data that's associated with blood sugar and insulin sensitivity measurements and the rate of diabetes. So what do we have here? We have BMI is one of the variables here. And we have here something called insulin sensitivity. IS is insulin sensitivity, right? Okay, so as you become as you get into pre-diabetes and diabetes, you guys know about a lot of you. I teach a lot of nutrition students and nursing students at Hunter, and they all know more about diabetes than I do because they study it so much. But insulin. I'm sorry. Yeah. Actually, tell you the truth, I think it's in with the lab stuff. I'll check though. Is it there with the lab stuff? No. I can put it on there. I'm going to put it on there right now. So if you want, you can open it up, work with me. I must have. It's there? Oh, it's in the lecture part. Okay, good. Yeah. Okay. So insulin sensitivity is associated with decreasing sensitivity to insulin. In other words, your body produces insulin, but it doesn't work well. Your body doesn't metabolize sugar well, so your sensitivity to insulin goes down. Changes in insulin sensitivity are related to diabetes. Now, the nice thing about you having this number, if you go to the doctor, he might run a blood test, and if your fasting blood sugar is over 100, right, he might say, you're diabetic. I want you to start doing this and doing that, and so on and so forth. So he kind of he's taking an arbitrary number, and he's saying, oh, it was 90 last week, it's 101 now, so suddenly you became diabetic. Or if it's somewhere very close, he might say, now everybody I know is pre-diabetic now when they go to the doctor. So whatever ranges they're using now, they're getting a little bit more selective. So at any rate, he's picking a number out and telling you you're pre-diabetic, you're diabetic, and so on and so forth. A more accurate, since it's a continuum, in other words, you're not diabetic one day and not diabetic the other day, your body is becoming less able to metabolize sugar properly over time. So insulin sensitivity is a nice measure because it's a continuum. In other words, you can see how it's going up rather than just all of a sudden one day was one or the other. So it's a little bit better measurement for us to judge how the relationship might be with some other variables. So we have insulin sensitivity. We have a number of subjects that we have these measurements for. We also have measurements for those same subjects for their BMI. So let's say we say to ourselves, well, gee, perhaps there's an association between BMI and insulin sensitivity, a measure of your status in terms of diabetes. Okay, so they're both numbers. They're both numerical variables. You can see that down here on the left side, as is most of this data. So we have data for, it looks like 33 subjects. We have their BMI and we have their insulin sensitivity. So now I want to see first, is there a correlation? Is there any association at all? So what's the best way for me to get a good picture of that? Yeah. Scatter plot. Let's do a scatter plot. Okay, yeah, graphs. I like using legacy dialects because I am a legacy. So I go down the scatter plot. I'm going to choose a simple scatter plot. Notice that matrix one that's next to it. That's how you put in variables where you can put in multiple variables and get, like BMI versus insulin sensitivity, and then some other measure versus BMI and insulin sensitivity, and so on and so forth, and get a grid. But we're only comparing these two numerical variables. So I'm going to move either. Well, I can move either one into the either axis. I'm going to get into the habit, though, of putting the one that I think is the cause or the independent variable, BMI, into the x-axis, and having the dependent variable or the result, which is insulin sensitivity, in the y-axis. And then I'm going to go click OK just to get a quick look at this. Okay, that's what I've got. So, pretty cloudy, right? You guys see in there somewhere, do you see like kind of association there? Look carefully. Right? Looks kind of bare down here. It's kind of bare up here. Looks like there's an association. As BMI goes up, what's happening to insulin sensitivity? It's going down. Is it a strong association? Well, it's pretty strong. I mean, these get pretty low, but those are all the way up there in that corner. But, there's a lot of variability in this, right? In other words, people with same BMI, like in the middle here, these people over here, 24, all of these guys will have all the same BMI. Look how much variability there is in their insulin sensitivity. So it looks to me like there's going to be a significant correlation. It may not be a real strong one, though. So one of the things that we can do, one of the little cheats that we can have here, is that we can double click on this graph, and it opens up an editing table, an editing window for this graph. And one of the things that you can do is one of these little bars here is add fit line at total. That's actually going to give us our correlation line or our regression line. I'm going to click on it, and I'm just going to click on it and say okay. Just click it away, and there, it's the one called fitted total. If you hover over it, it'll tell you what. What's that? Yeah, sure. I'll undo this. Undo. How far back should I go? Well, I'm going to close this first. I'll go back right to the beginning. Okay, here's our scatter plot. I'm going to double click on it. It's going to open up an editing window. In this editing window, I can go in here. I can edit the fonts. I can change the color. I can change the background. I can put a title in and stuff like that. You can see all this stuff on top here, right? So I can do all sorts of stuff in here. So now, but what I want to do is, you see these little, on this little menu bar over here, you can see show data labels. Okay, if I click that, oh, wait a second. Oh, show data labels is the labels on the side. This one over here is, let me hover, show error bars, add markers. I can add markers. This one is add a fit line. It says fit line at total. Don't worry about the add total, but add a fit line. That fit line is our correlation line. I'm going to click on that, and it already says attached label to line, and it's already set up to do this. In fact, it already did it in the background. If I close this window now, it'll put it on our graph as well. So ignore that formula for a second. Make sure you don't see that. That's actually our regression formula. But don't worry about that right now. So what did this do? This created a line which is the best fit for this data. So yeah, it looks like there's a correlation here, right? Now let me ask you something. If I have all of these spots here, and they all line up, and I got a straight line, and every spot is very close to that line, it's straight across. Is that a good correlation? No, it's not. Why not? Well, it's not a good correlation because as x goes up, y doesn't change at all. right? So it's not any kind of correlation at all, even though they all line up. X doesn't have any effect on what the value of Y. Even if it's a little tiny slope, you could have a very good correlation, right? But if it's dead flat, there's no correlation, zero. If all of these are kind of a blur and there's no shape here at all, you'll wind up in a horizontal line also because they're all balanced on the top and the bottom randomly. And that'll be zero correlation as well. Okay, but this one seems to have a bit of correlation. Okay, we see a couple of numbers here, R squared, we see that formula and stuff like that because it got a little bit ahead of us. Okay, so it appears to me that there's a correlation here. So let's actually go ahead and test this. So we're going to do something called Pearson's correlation or Pearson's R. Analyze, and we actually have a choice here called correlate. Correlate, bivariate. Okay, and now we're going to we need two variables to put in, two numeric variables. I'm going to put in BMI, insulin sensitivity, BMI, and insulin sensitivity. It doesn't matter what order I'm putting them in because it's only going to do a correlation, not a regression. Okay, but notice that if I only had one of them in there, the OK disappears. I need both of them in there, and they both have to be numerical variables for this particular analysis. So I'm going to click OK. It's going to perform this analysis for us. Okay, now what's the result that we got? Let's see the result that we got. The result that we got was that the association, if I compare BMI to BMI, the correlation is 1. I'm just, it's just doing something to itself. Its correlation is 1. Compare BMI to BMI is 1, right? But if I compare BMI to insulin sensitivity, the result is negative 0.548, negative 0.55. Is that a good correlation?
Yeah.
Well, what's a bad correlation? No correlation is zero, right? A really good tight correlation, a close correlation, would be, perfect correlation would be 1. In other words, if you know one value, you know the other one completely, right? So that would be one. You probably rarely ever see that unless it's a mathematical formula, right? Like, for instance, the BMI and person's weight probably would give you correlation 1 because it's part of the formula for BMI. But that's a whole other thing, right? So 0.55 is pretty good correlation, but it's a negative number. What does that mean? It's sloping downwards. It means it's a negative association. As one goes up, the other one goes down. As your BMI goes up, your insulin sensitivity goes down. In other words, your body is less and less able to metabolize sugar properly, right? You're not as sensitive to insulin. Okay, so notice it, like everything else, it repeats it twice, right? It's insulin sensitivity compares it to BMI, and you get the same number. And when it compares it to itself, you get 1. Now, is that a significant correlation? What's this value is called R, Pearson's R correlation, right? Or rho, it's rho or R. What's our null hypothesis? Our null hypothesis is that there's no correlation between these two values. Or in other words, R is equal to 0, right? That's our null hypothesis. What's our alternative hypothesis? R is not equal to 0. No prediction about how big it is, how small it is. It could be 0.001 and still be significant, statistically significant, and it could be 0.8 correlation, negative 0.8 correlation, but not be statistically significant. In other words, you might not have enough data to say for sure that it's really a correlation. So in this case, what's the significance? The probability that we'd be wrong if we reject the null hypothesis, 0.001. Since usually we're satisfied with anything with an alpha less than a p-value less than an alpha 0.05, we reject the null hypothesis. We say there is a correlation between these two, and the strength of the correlation is 0.55. Okay, so that's good. That's nice. We know now there's an association between the two of these things. Now let's quantify it. So I'm going to go to Analyze. I'm going to go, instead of going to correlation, remember, now I went correlation bivariate because we use two variables. I'm going to go to regression. I'm going to go to linear regression because we're assuming to start off with that the association between these two things is a linear correlation. Not that, for instance, that BMI, up to a certain point, a low BMI only a little bit of insulin sensitivity, and then all of a sudden at a certain point it just takes off asymptotically, right? This wouldn't work for that kind of relationship. Only works for relatively linear association. So we're saying we're going to do a regression, linear, and now notice it's not one box anymore. Now we have to identify which is the causative variable, right? So in the independent variable, that's where our BMI goes, right? Everybody agree, BMI? And in the dependent variable, in other words, the result of change in BMI is change in our insulin sensitivity. Okay, so I'm just going to leave it as it is because it's going to do our correlation. And I'm going to say OK. Okay, and let's see what we wind up with. I'm not going to worry about coefficients there. There we go. Here's our R values here. Okay, so what's our R value? Just as we saw in that graph when we did the correlation in the scatter plot, the R is 0.548, right? And then it does R squared. We're not going to worry about that for now. We're going to worry about that a little bit more when we take a closer look now with regression, right? It's 0.3. And our adjusted R square is 0.278. Okay, well, that's pretty interesting. Let me take a look at this. Okay, so I'm just going to look at R squared for right now. Predictor is BMI. Okay, so, gee, I have just what I got, just what I was expecting to get from our correlation. Now, as far as statistical test is concerned, we have we also did when we calculated when we did regression, we not only recalculated our R value, but it also took a look at that fit line and it determined what the formula was for that fit line, right? So so how did it do that? What it did was it took that fit line. Let me go back to the line. Okay, the way R was calculated, it takes the difference between the line and where that point is, and divides it by the variability for the BMI, and then tries to balance the line so that all those numbers are balanced on either side. When it calculates the regression line, what it does is it basically takes this distance, how far off it is. We call that's the error. In other words, if we were looking at the y-axis there, right? Our line predicts that if your BMI is 18, your insulin sensitivity is 0.8. Well, for this person it was actually 0.7. For this person it was 0.95. That difference between that, where we should have been on that line, and what that person's insulin sensitivity actually was, is called the residual, or error. You'll see it in the formula. It's that kind of little e, right? As the error. That's the error. What it did was took all of these errors and it balanced this line. So if you took all of the errors and squared them on both sides, it balanced those two numbers. So there's only one number, one line that fits that criteria. And everybody agrees that's the criteria that you use. That's why Professor White was saying, well, the line of regression, if we just did it visually, right, everybody would have a different line. If you do it numerically using these sums of squares, balancing these sums of squares of the errors of the residuals, well, then everybody winds up with the same line. Okay, and this is the formula for that line. So what is the formula for that line? Okay, let's go back here to our output here. If I go down here to coefficients, the very bottom there, you'll notice that it predicts that the slope of that line is going to be negative 0.043. In other words, for that much of a change, that the slope of that line is going to describe the change in BMI and the effect that it has on insulin sensitivity. It's negative, so the slope is negative, so it's going down. That predicts the rate of change. Well, now we know that the slope of the line is like this, right? And now we want to say, well, gee, that line could be anywhere on this graph. We have to pin it, right? That slope has to be pinned. It's going to pin it where it crosses the x-axis, where x is equal to 0, where it crosses at the y-axis, the y-intercept is where x is equal to 0. At x is equal to 0, y is equal to 1.582. that chart back because it actually did it for us. Actually didn't do it for us. Okay, so if you look over here, the slope here is 0.04, right? That's the slope. In other words, for every one that BMI changes, right? That, in other words, the slope is the change in y over the change in x. So for every 100, for every 4 that BMI changes, y changes. Let me do this differently. For every 1 that x changes, y changes 0.04. So for every 2, it changes about 0.1. Right? So in other words, 24, if I go from 24 to 28, it's going to change about from 0.6 to 0.7 or something like that. That's our slope, right? That describes our slope. It's negative, so it's coming down. Okay, so that gives you a measure of how much the change in the x-axis affects the value of the y-axis. But where does it cross the y-axis? At the point where x is equal to 0, it crosses at 1.58. The problem here, the lowest number here, the lowest person here is a BMI of 18. No one has a BMI of 0. So that's kind of an artificial number, that's 0. Don't worry about that y-intercept, because that y-intercept is over here, and it's up near the ceiling or something like that, right? Where 1.58 would be on this scale, right? You can see that it's going to continue to go up there, and the 0 is going to be here. It's going to cross it way up there at what number? At 1.58. Do we care about that number? Not really. It doesn't really tell us anything about people that are less than 18 or higher than 32. Regression, correlation, you stick to making your predictions only in the range where you've collected your data. You don't use to make predictions about people with BMI of 40 or people with a BMI of 11, right? Because it's not going to be dependable there. You stick to the range where you actually have the data. And in fact, the y-intercept is really just a number that pins this line for you, so you know what you can describe the line. So how does this help us? Well, first of all, is it significant? Okay, and since the thing we're really interested in here is the slope, because the slope will help us to predict a person's insulin sensitivity. Right, okay. So let's see, insulin sensitivity is 0.043, and our t-test for this, or simulated t-test for this, or the regression test for this, is a significant of 0.001. Same value that we had before. Okay, so what does that tell us? That our slope, that our null hypothesis is that the slope is 0. Our alternative hypothesis is that the slope is not equal to 0, or in fact, in this case, equal to that. So we can say with 95% certainty, less than 5% chance of being wrong, that we can rely on that slope value. Okay, so that's going to be our slope value. Now, there's ways to get a confidence interval for that. I'm not going to bother with that. I don't think that's going to come up for you guys for the most part. But we're going to use that number now to do a prediction. I'm going to pull up Excel. Oh my goodness, it's already 7:50. Shit. Okay. Okay. We went long tonight, right? Okay. So anyway, I just wanted to just show you right now. So I'll explain it to you. Let me get this out of the way now. Okay. Basically, if I take this formula that we just created, right? If I take that formula that we just created, and I ask you, gee, it's really expensive to run an insulin sensitivity test. But if you walk into my office, I can calculate your BMI very easily. So you walk into my office, your BMI is 27. Instead of running an insulin sensitivity test, maybe I'll just plug it into this formula, 0.04 times 27, whatever that comes out to, subtract it from 1.58. Oh, I think your insulin sensitivity is likely to be 0.95, 0.8, 0.7, whatever it comes out to. Would you really use it like this? Probably not. More likely you would use it to determine, well, if I can affect or get people to reduce their BMI, this is the kind of effect that I would have on their insulin sensitivity. So this is the value of, well, gee, I do a study and I find out that if your insurance company pays for your Weight Watchers or your exercise program, and they can demonstrate that it's going to reduce your BMI by so much, well then maybe they can make a prediction on what your insulin sensitivity would be using this graph, and they would be able to convert it to the cost of treatment for your diabetes if you develop it long term. So they could use this slope to decide what the payoff would be in public health dollars or insurance dollars. Right? Makes sense, doesn't it? That's linear regression. Multiple linear regression, what we just simply do, we add in another variable in our, remember there was a small box dependent variable, only one dependent variable, but you can have a big box with several independent variables and add them in there and see if they have an effect in here. So for instance, I could add in a second variable and see if my R value goes up, right? That R and R squared. That R squared is an important number.
Do you have to do a scatter plot?
Don't have to.
Before you put in the variable?
Don't have to. It's just
linear?
Yeah, no, you don't have to do any of that stuff. That's only nice because it'll help you visualize what's going on, but it's irrelevant to the actual calculation. That R value, if the R value is 50%, the square it at is 25%, 0.25, 0.5. That 25% is how much of the variability in one value is reflected in the other value. In other words, 25, in our case, it was about 50, 60%. Let's say it would have been, 30% would be our R square. 30% of the variability in insulin sensitivity is predicted by your BMI. 70% is predicted by other factors. But in public health, that's, like I said, 30% is big, right? This predicts 30% of what your value for insulin sensitivity is going to be. That's big, right? So you can combine it with other things. It might be age, might be X amount, the X amount that you exercise, amount of carbohydrates you eat, and so on and so forth. So it could be many other factors, and you can add those on. And what will happen if you select your variables correctly, that you really find other variables that are not directly related to BMI, but are different things, like the amount of sugar that you eat or something like that, or your age or something like that. You put all those in there, but what will happen is when you run this same analysis, your R square value will go up.
But you only get one R.
You
So you have to add them one at a time to see how much it increases R?
Well, you so you get an individual, R is individually for each individual. You get one R, right?
You get one R.
You get one, well, each time you calculate, you get different R and R squared.
Right, and so you can determine the difference
Right.
between those.
Right. So in other words, if you add in this variable and it doesn't help, it's not helping you. It doesn't contribute to your formula and give you more information. But you might go from 30% of predicting the variability in insulin sensitivity to 50 or 60%. So yeah, you're in great shape. You're predicting most of the things that are causing people's insulin
So would you
sensitivity.
do this stepwise? Would you start with one and you
I-
add one
I
and
would
you
con-
add one
I would
and you
consider-
add one?
I would
to see
consider,
what
yeah.
happens
I'd also add them in different orders,
Oh,
right?
okay.
Because remember, she said, well, this one is over here is dependent on this one over here and this one over here. So I might actually experiment with them in different orders as well. So let's call it a night. I think we recorded everything here. So I'm sorry that I lost track of. We started so late that
Yeah.
I lost